Okay, good afternoon, everybody. Thank you for coming to this seminar. It's a great pleasure to welcome here today Dr. Joan Bruna from the Statistics Department at UC Berkeley. Dr. Bruna graduated from the Universitat Politecnica. It's probably like positive feedback there somewhere. Sorry. He graduated from Universitat Politecnica de Catalunya in math and electrical engineering, and he also got his master's degree in applied math from Estrach outside Paris. And then he went on and became an engineer in a startup in the Paris area. And then in 2013, he got his PhD in applied mathematics at École Polytechnique in France under the supervision of Dr. Stéphane Malat. And he had a postdoctoral stay at the Courant Institute under Yann Lequin's supervision. And some of you know Yann, of course, who visited us a couple years back. And then he went on for a short stay at Facebook Research in New York City. And he's been at UC Berkeley as an assistant professor in the stat department. And I think he's also affiliated with the EE department, ECS, I should say, since January of this year, 2015. His research interests actually span a wide area of information sciences, including stochastic processes, harmonic analysis, and deep learning. And today, he'll be talking about signal recovery from scattering convolutional networks. And for those of you who are into deep learning, you probably have something to say about that. And thank you for coming.
Yes,
and it's a pleasure to have you.
Thank you for the great introduction. Can everyone hear me well? Yeah? Okay, good. Okay, so today we'll talk about not just how can you do classification or like awesome machine learning.
You have to stay away from the behind.
I need to see this. I need to see where I'm.
Well, you can look. You can look.
Here?
Yeah.
Okay. What we'll try to talk about today is not only one of the nice things you can do, like applying deep networks to solve machine learning problems, but also if we can say some things about the mathematical properties, what sort of, like from more signal processing perspective, what are the properties that we get out of this deep convolutional network? So we'll try to go slowly, and of course, if you have any questions, just stop me and then. Okay, so just to give some background to frame a little bit what we are going to talk about. So typically, I guess you have heard in the latest years, there's this like big data explosion. We have now these networks, they can be trained on more and more data. One of the arguments that I consider that is also changing and is something that is useful to explain what's going on is also that the tasks that we are considering are now more and more complex. Okay, so something very classical from, I'm assuming here that a lot of EE people, compressing, denoising, these are tasks that we have been dealing with for many years. Okay, these are also dealing with complex data, except that the task is probably not so complex, right? I mean, we know how to basically solve this problem is considered essentially solved. But then we can make the problem a bit more complicated. For example, super resolution is like already a bit more challenging inverse problem, in which probably we need to incorporate a little bit more structure. We have to change a little bit how we define as a good solution. Then something that is now more the territory of machine learning is the problems that I call pattern recognition. So simple pattern recognition problems like this one are problems in which you have part of your data that is for which it's very hard to build mathematical models, and so for which you might want to train, you want to learn things from data. But there's also a part of the problem that has a very clear, a very simple mathematical structure. In that case, here, for example, we can model the variations we have in the data set as being, for example, changes of elimination changes in point of view. In the case of speech recognition that you see here, we can model very well the variability that comes from saying something as a transposition in the time frequency space. When we write something, when we write digits here, we have a clear variability that comes from different drawing styles that can be modeled correctly using, you will see, like reasonable mathematical tools. But then the problem gets more and more complex. Here we are in the world where it's already super hard to model what's going on mathematically. We have, of course, we have the same problems that we had before, like translation, illumination, point of view, etc. But we have like a much higher order of magnitude of problems, right? The variability, trying to model the variability between this object and this object. If you want to do it from first principles using math, I'm sure you're going to have a hard time, right? I mean, you really need to. It's really a task that is much more complex, and it can get even more complicated. I mean, this is one of the things that we are doing, people are doing right now in using deep networks, try to, for example, map an image to a sentence. Okay, not just trying to classify what is the label, but also trying to come up with a reasonable answer, with a reasonable caption to a given image. Okay, so in all these problems, sorry, I have to stay in the left, sorry. So what I would like to motivate here is that for every task, you have a natural way to compare signals, right? We at every time, we need to change our notion of how do we measure signals, how do we compare things. Okay, so, and one of the things that we will try to do is to think about this distance, how to compare things. We'll try to make things a bit simpler, right? So put everything into some fancy Euclidean space, okay, with this representation phi, and then the distance is just going to be Euclidean distance, okay? And that's how we can use everything we learn about linear algebra, how to actually learn. I mean, the way we think about distances, the way we can do easy geometry is when everything is Euclidean. So we'll try to capture all the structure of the problem into learning a reasonable representation phi that will capture, as you see, that probably will have to change from one task to the other. Okay, and these are the sort of the questions that we are going to discuss along this talk. Okay, so as we make the task more and more complex, how much information can we keep? How much information can we lose from our signal? Another motivation, another thing that is now very popular these days is how do you construct what we call a generative model? Okay, so, and this is something that is more in the realm of what's called unsupervised learning. Okay, so you observe a lot of data. How can you make the computer imagine new data? Okay, that comes from somehow captures some of the properties that you care about. So one way to approach this problem is to say, well, let's say that I have this super fancy representation phi that has been able to extract, in the case of like ImageNet or image recognition, that is able to classify things correctly, right? In a sense, we started from this high-dimensional space where everything is very, very messy, everything is far from each other. We have a representation phi that somehow is able to put some order in this mess, right? To, for example, say that all the cars are in one plane and then all the dogs are in another plane, etc. So the question is, if we start from this setup, probably in that space we can start to do sampling, we can start to do like interpolation. Okay, we can do simple things in that space. Another question is, well, is there something such as the pullback? Can we take these samples here and move them back to the original space so we can sort of hallucinate that we can generate new samples? So that's one of the questions. That's the motivation of the talk. And of course, this thing has applications that go beyond classification, right? If we want to do like super resolution, or we want to sort of solve something in the original space, maybe we can try to add some priors, like replace the priors that we know, for example, sparsity, right? Sparsity is a prior that has been very powerful in signal processing in the last times, right? Sparsity is it's in a sense building a particular generative model for data. So how can we go beyond sparsity using these powerful nonlinear representations? That's one of the questions that motivate. Okay, so we are going to try to discuss about these problems today using something that we call scattering convolutional networks, that I will explain in a minute what this is. And then we'll discuss some more, I would say, mathematical properties of these representations that I call signal and texture recovery. And then we'll see some applications to this. Okay, so let's start with a simple, like the first step. It's like in the
first slide, remember, like this axis, we are somehow in the middle now. Okay, so we are in problems where we have to perform some form of like pattern classification. Okay, and in that problem, the sort of variability that we should expect from our data is something that is much more, in a sense, much more sophisticated, much more dangerous than just adding additive Gaussian noise. So how can we model this variability that we have in this problem? Well, something that we call geometric variability. Okay, so here if you model your data as being like images, so here, let's say that here, just for the notation to be clear, you can think of as your data as some functions that are defined on some grid of pixels or on some grid of time samples. And then what we're going to define is this way of adding noise to your data, but just that rather than being additive, it's like noise in the form of warping. Okay, in a sense, it's a geometric noise. Okay, so the sort of things that you can model with this are the sort of deformations that you see here, right? By stretching things, okay, you can model variability. That, for example, if you are trying to classify digits or you are trying to classify, I don't know, things on the wild, okay, that's something that you really need to take into account, right? Because, for example, if I go from this object and I change it a little bit or rotate it a little bit, well, you cannot really model this as adding additive Gaussian noise, right? You can model this by doing a change of variables, okay? And so how are we going to define the notion of how much noise that we are adding? Okay, so we need to define an equivalent of what's the amount of noise. What's the equivalent of the PSNR, right? If you are EE people. So one way to do it is to define what I call a deformation cost, right? For how much I'm going to deform things. And so one reasonable way to do it is to consider like a norm, what's called a norm in that space of diffeomorphisms, that somehow penalizes by how far I'm going to move things, but also by how much I'm going to stretch things. Okay, so if you look at the gradient of the deformation field, it's something that measures if I move things in a very rigid way, in which case this is going to be very small, or if I start to break, to share, and to compress things apart. Right? And we all agree that, for example, if I move from here to here, it's a bit less dangerous than if I move from here to here. Right? And here, that's something that can be well captured by the amount of deformation that I apply. Okay, so how can we deal with this sort of variability? Okay. Well, there's one, many fields in signal processing. The first thing we try to do is how can we find the linear model or like the linear transformation that is going to be consistent, that's going to be compatible with that model of variability, with the deformation variability. Well, it's very easy to see that the only operator that is consistent, that is compatible with this form of noise, is to blur things. Okay? You can imagine yourself, like you draw a line, like a signal. If you want something that is going to stay basically the same as you deform the signal, well, you have to blur it. Right? If you blur, things are going to be more stable to deformations. Okay? So, and actually, it's very easy to prove that it's the only one. Okay? So blurring is the only thing you can do if you stay linear. Okay? But of course, blurring has a big problem that loses a lot of information, right? All the high-frequency information is thrown away. And we know that for example, our brain, the way the cortex works, is super sensitive to high-frequency information, right? We cannot afford to waste, to lose this high-frequency information. So how can we formalize, how can we complete this information that is lost by this blurring operator? Well, there are amongst the many different ways to do it. One that is particularly interesting and that we'll see that has good properties is to recover this information with what's called a wavelet filter bank. Okay, so wavelet filter banks are just a fancy name for a bank of filters that is baseband. Okay, and it has some selectivity across different scales and different orientations. And we have evidence that this sort of filter bank is happening in our cortex, in our visual cortex. We have these sort of cells, okay, that somehow are selective to different orientations and different scales. And most importantly, they are able to capture the information that is lost by the blurring. Okay, but of course here we have a problem, because I told you that linear. So this is still a linear operation, right? And I told you that the only linear operation that is good, that is stable, is this one. So therefore, this guy here, these coefficients here, are not going to be. I cannot plug them directly into my classification engine. They are not going to be stable to deformation. So what do we have to do? Well, a very simple consequence of this is that we really need to go nonlinear, right? We really need to take these coefficients and apply something nonlinear. And so it's another thing that we can derive and we can prove is that amongst all possible ways to transform nonlinearly our signal, one class of nonlinearities that is particularly powerful and very nice and has very good properties are what we call the pointwise nonlinearities. Okay, so the pointwise nonlinearity takes a whole vector and applies the nonlinearity pixel by pixel. Okay, so it doesn't try to combine things across different pixels. It can stay local. Okay, and these nonlinearities have good properties. And in particular, they have this commutation property that it's called, and we will see why is that important. And the way you can see this thing operating is that it takes energy that lives somehow in the high frequencies. And when you demodulate, I mean, people who are working in E, they know, right? I mean, if you do a full rectification, half rectification, what you're doing is you're bringing your signal, your energy, back to the baseband, okay, where this operator is going to extract information again. Okay, so that's the basic three ingredients. And in fact, these three ingredients have already been used for engineers and people working on these models since the 90s, since the 80s, right? I mean, something that people have been using for extracting audio features, that's called the Mel frequency spectrum, has exactly the same multi-resolution wavelet structure. Okay, so the thing they do is that they consider a filter bank where the filters, so the bandwidth of the filters, increases with the central frequency. And then out the output of this filter bank, they apply a point-based operator. They just estimate the energy. Okay, so that's how the Mel frequency spectrum coefficients are computed. Same thing for images. This is something that was very popular 10 years ago. Okay, the SIFT descriptors, they do the same, right? They start by extracting local coefficients that are selective to orientation, and then what they do, they apply this local averaging. Okay, so they compute just the local histograms of oriented gradients, and this is how they construct the descriptor. Same thing here, convolutional networks. Now, so if you are not familiar with convolutional networks, you should. Okay, very soon, because they are going to be everywhere if they are not already. And so if you look at convolutional networks, what happens in the first layer, okay, so the things that they learn at the first layer resemble a lot a sort of fancy wavelet filter bank. Okay, so you can see here some filters that are selective to some orientations, different scales. Of course, here they also are able to extract information across the different color bands, etc. Okay, so this operation is everywhere. Okay, so the first operation is everywhere. Okay, so how can we now define our scattering convolutional network from these first principles? Okay, so usually this should be an animated slide. Since I changed to PDF, it's not, but okay, it doesn't really matter. I will explain it like this. So it starts with an input signal F. The first thing we do, as I described, is compute our stable linear operator. So this is just taking our signal and blurring it a little bit. Okay, so here J corresponds to the scale in which we want to blur things. Okay, so if we just do this, that would be a linear operation. What are we going to do next? Well, we are going to recover all the information that is lost by this blurring by a bunch of filters. Right? These are the wavelet filters that are going to recover the information that is missing from the first layer. What are we going to do then? Then we are going to demodulate these wavelet coefficients, okay, by applying this pointwise modulus operation. And then, once we are here, well, we have again a signal that has energy in the baseband. So what we're going to do is we're going to apply again the same operator that we described before. Okay, so we are going to take each of these signals and reapply our blurring operator again. Okay, and of course this operation again is going to miss some energy. Okay, it's going to remove some energy that is going to be recovered by this new family of wavelet decompositions. And so now you see that this operation can be repeated again and again and again and again. And the result is that at the output of every layer, we have coefficients that are the result of some operator that is stable to deformations. Okay, so that's how the scattering network is defined. And so thanks to the let's say the mathematical properties of wavelets, and as I described, the things that we can prove about this blurring and demodulation operation. Well, first, before showing you the theorem, let's try to get some intuition on what these coefficients are capturing. So here, it's a very simple example that illustrates, it illustrates how are we encoding information. Okay, so here you have a bunch of, you have two different patches. Okay, if you look at, so think about this as like two localized patches in an image. Okay, so if you look at the shift coefficients, I recall, shift coefficients are just measuring the average energy that I have along different scales and different orientations. Okay, so I have a filter bank that is selective to scale and orientation. I look at the average energy that I have along each patch, and that's how I construct my shift descriptor. Okay, so if you see what happens here, the shift descriptors are the same in these two patches. Okay, and actually that's not coincidence. I mean, that's an example that illustrates exactly what sort of information do you lose by this operation, right? By blurring here. So the average energy of this in these two patches across all the scales and orientations is the same. But the way this energy is distributed in space is very different, right? In one case, the energy is like uniformly spread along all the locations of the patches, whereas here it's concentrated, it's very sparse, right? So where is sparsity being encoded? Well, sparsity is being encoded in our scattering network in the second layer. Okay? So the second layer is going to tell us how this average energy is going to be distributed in space. Okay? So you see that sparsity is a very important principle to describe natural images. Here we have it. We see it as a natural principle that tells us how the energy is going to decay along this tree. Okay, things that are going to be very sparse are going to have a particular decay that is going to separate them, distinguish them from things that are not sparse. Okay, so here there's no animation. Sorry. Well, too bad. So here, I mean, we are able to prove actually that these coefficients are indeed stable to this deformation that I described before. Okay, so here this should be a movie that illustrates that when you have this little pattern and you deform it and you stretch it a little bit, you see that the energy in the scattering domain is stable, right? It doesn't move all over the place. Whereas if you look at what happens in the energy in the Fourier domain, you will see that the energy is jumping all over the place. Okay, so this is like an important thing, and an important point here is that as opposed to like a spectral decomposition of the signal, here we have stability to deformation. Whereas if you just look at the spectrum, of the power spectrum of a signal, it's not going to be stable to deformation, right? Because the high frequencies are going to move a lot as soon as you start applying something that is a non-rigid deformation. If you are interested, I can show you the picture, the animation later. Okay, so that's for how we define the scattering for like images for let's say deterministic functions. We can actually we have to also consider what happens in the case of texture, stationary processes. So why are stationary processes an important part of computer vision? Well, the sort of, we are all able to tell very easily that these two things are from the same class, right? That these two things are from the same class and that these two things are from the same class. But if we start trying, how can we warp one into the other? Can we explain this as a deformation of this? Well, I'm pretty sure that it would be almost impossible, right? It's a complete mess. That's not the right model. It's not the right we have to introduce a new form of variability, a new prior of variability. And in that case, comes from the fact that the good model for this is to say that these are two realizations of stationary processes. And so in which case, we have to define our representation. How can we represent a stationary process? Well, we represent it as a bunch of expected values, right? So that's just a fancy notation to say you represent the texture by saying, well, I compute a bunch of complicated localized functions fi, and then I average, okay? I average across the whole image domain. Why can I average? Because I'm assuming that my input is stationary, right? So the statistical properties on these images, if the image is large, they should eventually converge. So what is the equivalent of stability that we had before? So here the equivalent notion of stability is the variance, right? I mean, these things we're assuming that are samples from a process. Okay, so whenever we estimate our representation, we are going to have an approximation, right? It's like an empirical. It's an estimator for this guy. So knowing how far is it going to be on average from the truth, that's the key, right? That's the stability. Okay, so if we have a very fancy representation for a stationary process, but we can never estimate it efficiently from the data, that's useless, right? Because when we will do classification, It's never going to be helpful to tell us that things are close to each other. Okay? So here we have identified an equivalent between the equivalent notion of discriminability and stability. So how are we going to define our network in that setting? Well, it's actually the same as before. So we start with our process X, and now the linear operator, rather than being blurry, is just taking the expected value. Okay, so that's a linear operator. How can we recover the information that is lost by this first moment? Well, we just need to look at the increments of the process at all different scales and orientations, and then take the pointwise nonlinearity. Once we have this, well, we repeat the same story. Okay, so it's exactly the same thing as before, except that now what defines our linear operator is the expected value. Okay, so for those of you who are familiar with, for example, high-order power spectrum, high-order Fourier analysis, in a sense, that's an alternative, right? So rather than completing the power spectrum that is covariance with high-order correlations, we are going to compute a bunch of nonlinear moments, right? So rather than having polynomials here, we have this modulus of wavelet coefficients, okay? And so we have a bunch of different processes here, and we stick with first-order moments. So why do we stick with first-order moments? Well, before answering, let's see what these things are able to do, what these things are able to capture. Okay, so that's another example that illustrates very simple what are the properties of these scattering coefficients on textures. Here you have, again, two different textures, and the way they are constructed, they have exactly the same power spectrum. Okay, so that's no coincidence. I mean, I just constructed this texture to have exactly the same power spectrum of this guy here. So if you look at what happens in the first layer of the scattering network, you will see that it's very hard to distinguish them, right? I wouldn't use these features to separate between the two textures, okay? But, of course, these two things have the same power spectrum, so they have the same correlation structure, but they have a very different high-order moments, right? In that texture here, that's a Gaussian process, okay? So a Gaussian process is a bit boring, okay, because the high-order moments are all predictable from the second-order moments. Here you have something that is super sparse, right? It's intermittent, so it has a very rich high-order moment structure. Where is this high-order moment structure captured? Well, you see it emerging again in the second layer of the scattering moments. Okay, so by doing this, the cascade of nonlinear wavelet transforms, we're able to extract high-order moments. Okay, and not only we're able to extract high-order moments, we are able to extract them in a stable way. Okay, so we have a consistent decomposition. What does it mean? It means that as opposed to just estimating these high-order moments directly, okay, as you would do with high-order Fourier analysis, here we can estimate these things, and we know that the variance of our estimator is going to behave. Okay, it's going to converge to zero. Okay, so we have this result that tells us actually that we're able to characterize not only the fact that the variance of these empirical moments goes to zero as we have more and more data, which is like the least you could ask. We also can characterize how fast it goes to zero. And what is interesting is that for this result to hold, we see that actually we need to have a deep network. Okay, so actually cascading a nonlinearity is necessary if you want to control the variance. Okay, if you just keep adding coefficients and you don't add layers, your variance is going to be, at least I don't know how to control the variance. Okay, whereas in that regime, it's something that you can control. You can still be consistent. Okay. So with this, what can we do? Well, we can apply these things to, as I said, somehow in the middle of the line of the first slide, a little bit to the right. Okay, so we can do pattern recognition very well. We have the state of the art. We can do texture classification. We also get state of the art. Object recognition. Okay, so for easy object recognition problems, that is here, that's a data set that has about 70,000 images, but they are small, 32 by 32, and you have 10 classes. Here, with these things, you get about 17% error. And just to give you the background, the state of the art is between 6 and 7%. Okay? So already you can see that there's a big gap, okay, with respect to the state of the art. Needless to say that the state of the art is using deep convolutional networks with a lot of training. And as you make the problem more and more complex, the gap only becomes wider. Okay? So here, what we see somehow is how far we can go by fixing the invariance by hand. Okay, so here, what we just constructed is a particular class of convolutional network that was good, that was constructed to be stable to these different sources of variability, right? One is the things that are like, they need to be stable to deformation. So I want, if my signal is a little bit warped, I want my coefficients to be close in Euclidean space. And if I have something that is stationary in the input, I want to have some provable guarantees that my representation is going to behave, right? But from here to the ImageNet or like complicated recognition problems, we have to add many other things on the wish list. Okay, so not only we need to be stable to deformations, we also need to know that, I don't know, that dogs appear in very particular positions. That, for example, that if we have to recognize a particular breed of dog, we have to focus on a very specific part of this object, etc., etc., etc. These things, we cannot construct them from first principles. Learning is necessary. Okay, learning is necessary. Okay, so but this talk is not about this part. Okay, so we are going to now try to look back, try to step back and try to understand or try to give some properties or conditions on what can we say about the recovery part. Okay, so not just problems where we just need to do classification, but also problems where we might want to go back to the original domain. Okay, so that corresponds to a lot of inverse problems. Okay, where we have to estimate some signal that lives in the original space. So how are we going to phrase this problem? How are we going to define this problem? It's very easy, right? It's like, given the set of scattering coefficients, or in a sense, the deep network or the convolutional network coefficients, the features here, if we compute them with a given number of layers and a given number of characteristic scale, when can we recover the input signal? Okay, so in other words, how much information are we going to lose by applying these nonlinear things? Okay, so with these nonlinear features, I told you that we have very good properties, right? We are stable to deformation. We are like locally translation invariant. And we have seen that we are able to characterize a little bit of sparsity. What do we lose? Okay, can we hope to recover exactly the same signal up to perhaps some translation? That's the first question. And the second part is, well, if I ask the same question, but now for processes. Okay, so now this corresponds to how can I characterize a process like an input distribution that is characterized by these scattering moments. And how can I sample from these distributions, right? How can I estimate these distributions? What form do they have? And how to sample from them, okay? Okay, so for the first part, what we know is that as we make the scale larger and larger, what we see is that we end up with a representation that has the number of coefficients that we capture is very, 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 very small compared to the input dimensionality. Okay, so if you look at how many coefficients I have in each layer, is something that depends essentially on the scale of the signal. Okay, so which is logarithmic in the number of pixels. So if I stop the cascade after m layers, I get something that is like just a polynomial on the logarithm of n, which is in typical regimes much smaller than the number of pixels. So here, the question that we are asking underlying is a compressed sensing question, right? It's like I have a very small set of measurements. In that case, are nonlinear. When can we recover the signal? Okay, so that's an equivalent. So that's a problem that belongs to the compressed sensing world. And there are some related results. There are some results by Yonina Eldar and co-authors where they studied a similar question in the case of the power spectrum. And there's some work by Roland Berchinin also trying to do something about the quantized random measurements. When we have a fixed scale, okay, this thing I described here is no longer true. And what we'll see is that we can have regimes where the number of features, okay, the number of scattering features, is comparable or maybe perhaps even larger than the number of input pixels. Okay, so in that case, you could ask the question, well, can you recover, right? You have a bunch of coefficients that are, the number of equations that you have is larger than the number of unknowns. Can this solution have a good unique solution? Okay, so this is a problem that is also known in the literature as the generalized phase recovery problem. And there's some work also related to this problem. And we have like both positive and negative results. And for the second part, for the texture synthesis, also, I don't know if you're familiar with these works by Simoncelli, etc., where they also ask the question of how can you estimate like probability, like high-dimensional probability distributions that are good to sample and to like apply both for images and sound. Okay, so let's just get deep into the subject. So the way I set up the problem, the recovery problem, is just to fix ideas. Here I have a given, I have a given set of features, y, okay, that are the output, so the scattering of some unknown signal. Okay, and now I'm going to try to find a signal x whose features are close to my target. Okay, so that's very simple. Actually it's very simple, but already you can see that as long as you start looking at what these features are doing, you see that intrinsically, like in essence, what we are trying to find is intersections of sort of weird L1, L2 balls. Okay, so here, think that this is like an L1 ball. So the first layer gives me an L1 ball. Here, what I have is sort of a mix between L1 and L2, because when I look at this modulus of wavelet coefficients, somehow these are like L2 balls. It's like a local energy. And then I have this local energy. I rotate it a little bit, and I look at the L1 norm. So you see, super complicated, right? I mean, that's something that a priori has a complex geometry. And of course, it's non-convex. So how are we going to, what can we say about in that regime? Well, the first thing we can prove is that we have a sort of an equivalent of a sparse recovery condition, right? It's like a sort of a humble version of what people in compressed sensing can say. So here what we can say is that when we have an input signal that is sparse in the sense that it's only supported in a bunch of points with a certain mass, if we have a condition that the separation between the peaks is larger than the support of the wavelet, okay, then the scattering coefficients of this signal are essentially everything we need to reconstruct. Okay, and the nice thing is that remember that the reconstruction that we have here, the thing that is interesting is that it's up to deformation terms. What does it mean? It means that we are not going to hope to reconstruct exactly a signal that has the peaks exactly in the right place. The peaks can be a bit moved, but the distance by which the peaks are going to be moved is controlled. Okay, it means that we are essentially we are tolerant to little deformations, but we are sensitive. Okay, we are very sensitive to like separations that are large compared to the support of the wavelet. Okay, so that's something that is like a positive result. Okay, so if in a sense, and here we are not assuming sparsity. Okay, so that's one of the important things. It's not that given these coefficients, assuming that the input is sparse, then we can recover. No, here the sparsity is encoded in the representation itself. Okay, in the sense that if there's no non-sparse signal that has the same coefficients as the one of a sparse signal. Okay, and you will see that this also generalizes in 2D. Okay, another thing that is also interesting is that not only we are able to recover sparse signals, we are also able to recover things that are highly oscillatory. Okay, so things that are sparse in Fourier, in a sense. Okay, so here we have it's basically the same result, except that you replace, a sparse measure in time by a sparse measure in Fourier. And the same thing happens if the spacing between the frequencies respects a certain minimum separation. Then we're able to recover a signal that has that respects the same thing, right? It's a signal that is sparse in Fourier, and the spacing between the logarithm of the frequencies is also respects this minimal separation requirement. Okay, so it's the same result as before, except that you swap time with frequency. And the important thing is that the measurements didn't change, right? It's like the same set of measurements is good to recover things that are both sparse in one domain and sparse in the other domain. Okay, and the way you can interpret this is that wavelets somehow sit in the middle between Dirac and Fourier. Okay, so since they are sitting somewhere in the middle, for them it's the same. It's more or less the same to look at things that are sparse in space or sparse in Fourier, more or less. Okay, so this is nice. These are some results. How does it work in practice? First thing to tell you is how are we going to recover? What is the algorithm that we use to reconstruct? Okay, to solve this problem that I told you that are non-convex and a priori hard to solve. Well, the way we do it is really a bit disappointing in the sense that the algorithm is super naive. Okay, so what we do is that we look at this cost function and we just do SGD, right? We just do a stochastic gradient descent on this cost function. And so what is interesting So yeah, the way it works, if you want geometrically, is that you start with some initial guess that can be just a sample from like random white noise, and then what you do is that you try to perturb this solution until it hits like a manifold of points that satisfy your constraints. Okay, so the way you go from here to here is by minimizing this energy. And the nice thing is that despite being a horribly non-convex problem, we have some weak convergent guarantees. Okay, in the sense that we can show that if you use like a second order method where you can actually afford to invert the Jacobian at every iteration, then you have some sort of a mild global convergent result. Okay, in the sense that you will always be guaranteed to move in that space. Okay, so you're never going to be stuck according to these conditions. Okay, so how does it work in practice? Well, that's a pity that it's not appearing well. Well, I'll show you the result. I'll explain the result. Okay, so here we have some examples that illustrate the sparsity. Okay, the positive recovery results. Okay, so things that are very sparse in space, and here we have something that, of course, is very sparse in the Fourier domain. So what we see is interesting is that if we have just one layer, okay, remember that one layer, the only thing we are doing is doing essentially a linear transform, right? We are doing a wavelet transform of our signal, and then recording what is the average L1 norm along each of the wavelet subbands. Okay, and then we are trying to find signals that satisfy this bunch of L1 norms. So what you see is that, of course, when something is sparse, okay, it's going to be like, in particular, these things are very sparse in wavelets. So if you reconstruct by just using the L1 norm of wavelet coefficients, you will reconstruct things that are sparse. Okay, so that's what happens here. That's what you see here. You are able to, in a sense, capture the essential geometric. So the crudest geometrical characterization is sparsity. Okay, so you are just able to recover sparsity, but nothing else really. Right here, it's very hard for us to sort of identify what's happening here. As long as you add a second layer, okay, you are going. Of course, you are adding much more coefficients. You go from log n to log n squared. The geometry appears very naturally. Okay, so the geometry, in a sense, is encoded very naturally, very powerfully, in the second layer of the transform. Okay, so remember the first example where you can see that if you just stay by looking at the average energies of different wavelet subbands, you don't have any way to tell how this energy is going to be distributed in space. As long as you're the second layer, you are still compressive, right? The number of coefficients here is still much smaller than n in general. But the geometry somehow is captured, like the essence of the geometry is captured. Okay, what else? Sorry. Yes. Okay. So another thing we can do is to rather than try to reconstruct by just looking at the global norms. Okay, we can stop the transform at a given scale. So this is for those of you who are familiar with like feature extraction, okay, or ConvNets. It's like saying, well, rather than looking at just a bunch of features that are completely delocalized in the image, we are going to stay at the patch level. Okay, so for every patch, we're going to extract some features, but we still know which patch we're in. Okay, and the scale, how large is the patch, is the scale, is this scale J. Okay, so what we should expect is that if the scale is very small, it's going to be easier to reconstruct, right? Because all this spatial sort of configuration of the image is going to still be preserved, right? So the question here is to see what happens as J changes. Okay, so as J increases, we have less and less redundancy, and here in that setup, we are not able to prove anything so far. But let's use the same gradient descent algorithm and see what happens. Okay, and try to analyze what happens. So here, what you see is indeed the following, right? If you start with, so these are the original images, and this is the reconstruction you get, okay, as you make the scale larger and larger and larger. Okay, so here in this column, I'm going to write what is the equivalent redundancy. Okay, so what is the size of the representation relative to the original? Okay, so n squared is the number of original pixels. So here you see that in that line, we are sort of redundant. Okay, we have more features than pixels, and when we reconstruct, everything goes pretty smoothly. Right here, you almost see no difference between original and reconstructed from this scattering coefficient. As you start to go compressive, okay, as you start to make the size of the patch a bit larger, things start to change a bit. But what is interesting is to see how it fails. Okay, so here we are trying to find a signal that somehow satisfies the conditions. Okay, so And this, the important here is that they tells us what these coefficients are encoding somehow. Okay, so you see that here, for example, like the wheel is not perfectly aligned, but the fact that it's something wrong is perfectly present in that reconstruction. Okay, so the geometric structure that it's still somehow present in these coefficients. Of course, when we have the patch that is too large, I mean, it's not able to actually to stitch it together correctly. Okay, but because of course, in particular, you see that here the sparsity prior that I described in the beginning is far from being respected. Right here in natural images, we know that we can find simple models where things are sparse, but if you try them in real life, it's not sparse. Okay, and here we see in a sense why this is happening. Okay, I should mention that this sort of algorithm is actually very similar to some of the recent works by people who try to do exactly the same thing, but by using like more fancier, beefer convolutional networks. And here you see that the reconstruction that they get is a bit impressionistic, right? This is before the deep dream things that appeared like 2 months ago. But still, I mean, if you looked at the images from the deep dreams, they also have something that is fundamentally missing from the original image, right? There's a gap. There's something that has been lost. It's more artistic. Yeah, it's more artistic. So depending on what you want, you might want to to accept that, okay, these features have lost something from the image. Well, they're still able to tell, there are some shapes, that there are some, so these things they capture, but there are many other things that they have lost, and we don't know what. Okay, so that's trying to fill the gap between these two things is one of the consequences, one of the usefulness of this work. Okay, so for textures, I believe, I have 5 minutes, a bit more. Well, okay, I'll try to hurry. Yeah. Okay, so for the textures, it's a bit similar, the same story, except that of course the math is very different. Okay, so now rather than looking for a particular signal that we want to reconstruct, here our goal is to define a probability distribution, right? What is the probability distribution that is defined by a bunch of moments, by a bunch of measurements that we have estimated from data. And the right mathematical formalism for that is what's called the maximum entropy distributions that are completely answered by the Boltzmann theorem. Okay, so it tells us that the sort of distributions that we are looking for have this form. Okay, so here we have a horrible normalization constant, and here we have a bunch of sufficient statistics that are given by our empirical scattering coefficients. Okay, and so this thing is a bit horrible, but when the input is ergodic, okay, so ergodic means that essentially the texture is going to start repeating itself eventually. We know that this distribution converges in some sense to something that is much nicer. Okay, that is the uniform measure on this set. Okay, so now this set is completely deterministic. Okay? It's a set of signals whose empirical scattering coefficients match the average of the scattering representation. Okay, so this is like I said, deterministic set. That is exactly the same set that we're landing using our previous algorithm. Okay, so the nice thing, so it's a complicated thing to show that the uniform measure here converges to this one. That's a complicated problem. But in practice, we can use the same algorithm. And here are some results. So here we have a bunch of textures. And in the first line, what you see is the result of just using covariance. Okay, so just you sample from a Gaussian distribution that has exactly the right covariance structure. Okay, so if you just stay with covariance, you are able to do very little. Okay, so you are able to, well, you see, it's essentially not good. What happens when you add the second layer of scattering coefficients? The geometry starts to emerge. Okay, so it's not perfect. Okay, you see that there's still something that you could tell that it's not quite right. For example, here and here. Here, perhaps it's not very good. But the nice thing is that here you have a very, very small number of scattering coefficients. Okay, the number of scattering coefficients is super small. Okay, so something quite essential is being captured. It's not perfect, but we see that in any case, going from here to here seems to be a big step. Okay, I have a slide with sound, but it's not connected. So if someone is interested, it's essentially the same thing with audio, with images, but with audio. Okay, so you see like sounds, and you see how I synthesize them using the first layer, and how they sound using the second layer. So for those of you who are familiar by reading spectrograms or scalograms, the bottom line is that this column is better than this one. Okay, so you see that we are able to reproduce things. Okay, but if someone is interested, we can play them later. Okay, so let me just finish with like a last application. How can we apply these things to super resolution? Okay, so super resolution seems to be a problem that now I'm going a bit left into my original first slide. Okay, so super resolution, I guess that is a problem that is super familiar to all of you. It's an ill-posed inverse problem. We can, of course, solve it by using a linear tool. That's the bicubic interpolation, essentially. But of course, we can also use a bit more fancier methods. So currently, the state of the art considers some form of dictionary learning. Okay, that's like the couple dictionary learning is one example. There are variants of this. Something that is a bit more recent is just brute force the problem. Okay, so have a convolutional network that is just going to perform regression. Okay, so you have a bunch of training examples, like pairs of low resolution, high resolution. Just treat it as a regression problem and hope for the best. And actually, what it turns out is that these things are actually better than these things here. And what they share somehow is that they try to optimize a sort of criterion like this, right? That is essentially trying to regress a high resolution signal with some estimate that depends on the low resolution and some parameters. Okay? And my claim is that this is a fundamentally unstable criterion. Okay? We have just seen that high frequencies are unstable to deformation, right? So let's say that I have a high resolution image and I apply a very small jitter. We know that in that domain, the target domain, I'm going to move very far, right? The Euclidean distance is going to be very far. But this guy is not going to move. Okay? So this criterion, what it tells us is that it's unstable, right? It's unstable to deformation. So one other thing we can do is to try to relax the metric, right? To change the metric in which we compare things and try to cast this super resolution problem in the scattering domain. Okay, so the way we do it is that we start by extracting our scattering features of the low resolution, scattering features of the higher resolution, and now we learn. Okay, so we learn, and we can learn with something as simple as just linear, like learning a pseudo-inverse. Okay, so there's no parameters involved at all. Of course, the only thing that we need to do at that point is that that's our input. We go here, we apply our linear operator, and now that we are here, we have to come back. Okay, and to come back, we use the inverse scattering that I described, the algorithm that I described. Okay, so just to show you some results. With this thing that is completely dumb, that has no parameters, no learning at all, we are able to essentially match or do even better than the state of the art. Okay, so this is the latest paper using this very fancy CNN. And so what we see here is that by changing the metric, by placing ourselves into a domain where we are, in a sense, building stability with respect to the variability that we have in our data set, where, the linear operator is able to actually get much more juice. Okay, so the high frequencies that were impossible to estimate using regression in the Euclidean domain, now we are able to, in a sense, extract some high frequency to put it in the right place because we have been able to stabilize them. Okay, so that's how I look at this result. Of course, the difference is not high, but here it's more like a proof of concept, right? That by relaxing the metric, you are able to do things easier and perhaps even better. And I think if I have 2 minutes, okay. So another thing that I want to discuss very briefly for those of you then maybe offline you want to discuss is that we have also another application to another inverse problem that is quite interesting. That is the audio source separation. So that's like the cocktail party problem. Okay, you sense like a mix of different speakers talking, and your goal is to separate the two different audio sources. And again, it's a problem that is ill-posed. Okay, we need to impose some structure into the linear estimate, into the estimators. We need to build like models for each of the different speakers. There are different ways people approach this problem. There's the blind. That's like the I would say the wild case where people don't even want to learn anything. It's like all the models are built from scratch. Then there's the discriminative setup where we can, for example, listen to one speaker alone Then we can listen to another speaker alone. We can build a model for each of the speakers, and then we try to apply these models in the real case, in the mixed case. Or there's the brute force model that I call discriminative, where I can just construct my own mixes. Okay, so I have a little bit of your recordings. I have a little bit of your recordings. I can artificially mix them together, and then train a model that has the ground truth, right? That knows the ground truth for this mixing problem. And if we just repeat this again, you can all agree with me that this setup seems to be the one that is most promising, right? The one that is, in a sense, testing things in real life. Okay? And so the same thing happens. The way people approach this problem is by extracting some sort of like time frequency representation, like some male frequency spectrum coefficients or some CQT coefficients, whatever. And then what they try to learn is some form of like an inference. Okay, they try to learn like a synthesis that is going to be adapted, that is going to try to separate the two speakers here. Okay? And then they are going to try to invert this time frequency representation to generate the two samples. Okay? And there are many ways people approach this problem. One that is particularly popular is the non-negative matrix factorization. And everything is all and good, except that, of course, if you want to impose good temporal structure, these things get more and more complex. Okay, so you can start with just separating at every frame, at every temporal frame. But then if you want to build something that is coherent across a larger temporal context, you need to make the dictionary learning, or in that case, you need to, in a sense, model the temporal dependency of this synthesis operator. And this is very hard because this step is very unstable, right? As we know, doing the sparse coding is an operator that is not stable, right? If I change a little bit my input, there's no guarantee that the sparse coefficients are going to be close, right? It's very unstable. So how can I build something that is like that incorporates stability, regularity, when you have this very unstable operation in between? Well, what we propose is something a bit slightly different. That rather than putting all this temporal structure in the synthesis part, we are going to put the temporal structure in the analysis part, right? In the time frequency representation, we can make it a bit more stable. Okay, and so it has a certain number of advantages. Now, in a sense, the synthesis is much easier, it's much more stable. The cons is that, of course, like inverting the analysis operator is going to be more complicated. It's going to involve the sort of algorithms that I talked about. Okay, but overall, what we see is that we get a good sweet spot, we get a good trade-off that shows that at least there's a clear advantage than doing it just on the original domain. And so that's like an alternative to using recurrent architectures that are like very, I would say, it's a black box and no one really knows what's going on inside. Here, at least, we have like something that is a bit more clean, that is a bit easier to understand, and it's competitive. So I think that, yeah, I said everything I wanted to say. And so, yeah, so if you have any questions or you want to listen to these audio clips, just let me know. And thanks for your time.